Yes, morning everyone. Welcome to another session of structural analysis. So in the previous class we have taken up non-sway analysis, right? So it was a complete non-sway frame. So today we'll take another problem related to sway analysis. So before going to sway, we'll take few expressions which will be useful for us in the calculation of frames which are subjected to sway forces. Okay. So I'll write the heading as sway analysis. Sway analysis. So the first case is, suppose for example we have a frame like this. So this case, we'll name this as A, B, C, D. Alright. So, and moment of inertia for this one is I1 and length is L1. Moment of inertia for this member is I2 and length is L2. So the moment ratios, okay, since this the end conditions are at different levels, isn't it? So when the end conditions are at different levels, what happened? It will be subjected to sway, isn't it? It is an unsymmetrical frame, so that is why it will get subjected to sway. So moment ratios is given as MBA by MCD is equal to I1 by L1 square divided by I2 by L2 square. So this will be useful for us in the calculation. How we will use this? We will check it at the calculation time only. Okay. So this condition is both ends. This is both ends are fixed, isn't it? Both ends are fixed. Another condition is both ends are hinged. They are at different levels. Moment of inertia for this member is different. That is I1, L1. And moment of inertia for this member is I2 and length is L2. So for this case, your moment ratio, that is MBA by MCB, we'll name it as A, B, C, D. So MBA to MCD will be equal to I1 by L1 square divided by I2 by L2 square. Both are same. Okay. When the end conditions are same, these two will be same. Okay. So another case is one end fixed and other end hinged. Other end is hinged. So this is I1 and length is L1. And this is I2 and L2, this is A, B, C and D. So in this case, MBA by MCD is equal to 2I1 by L1 square divided by I2 by L2 square. Able to follow? Wherever it is fixed, at MBA it is fixed, so we will be using what? 2I1 by L1 square divided by I2 by L2 square. Okay. Suppose for example, in another case, one end is hinged, this end is hinged and this end is fixed. So this is A, B, C, D. So what will happen here? MBA by MCD is equal to, this is I1, L1, this is I2, L2. So I1 by L1 square divided by 2 I2 by L2 square. It's very simple, right? If you see carefully, when both ends are hinged or both ends are fixed, then the moment ratio will be same. That is I1 by L1 square divided by I2 by L2 square. But you should not say it is same, because I value will be different for one member, L1 will be different for another member, isn't it? Similarly here also the same thing will happen. That means formula will be same, values may differ. Okay. Then for this case, since it is fixed here, so MBA will be 2I1 by L1 square, whereas your MCD will be I2 by L2 square. What about here? Here it is fixed over here. So here it will be 2I2 by L2 square, and in the numerator you will be have I1 by L1 square. Okay. Now finally what happens, in case of in your calculation of sway analysis, especially in moment distribution method, we have a formula. Okay, what is that formula? Suppose for example I need to calculate the final moment, that is MAB, capital MAB. Okay, so it is given as non-sway moments plus P by Q into sway moments. Now what is this? This seems to be something different, right? So what do you mean by non-sway moments? The calculation which we do in the previous problems. This is the calculation which we do in the previous problem. What is P and what is Q, we'll find out. It is very simple how to calculate P and Q. What about sway moments? Sway moments will get with the help of these ratios. Okay, it is very simple, no need to worry, but the thing is we have to calculate, we have to apply moment distribution table 2 times. Calculation of P, calculation of Q is very simple. Simply sigma x is equal to 0, sigma y is equal to 0, you will get those things. But the thing is you have to employ 2 times moment distribution table. In the previous problem we used to do only one calculation with final moments, but here you have to apply one more time using these moment ratios. Okay, copy down this one, then we'll move to the problem. So now copy down the question. Analyze the frame shown in figure, using moment distribution method. The frame is given like this. Height of this frame is 4 meters, so 4.5 meters, and this is I, and this is 2I, and this one is 4I, and we have a point load of 9.6 kilonewton. This distance is 1.5 meters and this is 4.5 meters, and we have a UDL over here. And the intensity of this UDL is 8 kilonewton per meter. Okay, this height, if the height is same, see here the height is 4.5 here also and here also, the span is 4.5, 1.5 means 6 meters totally. Okay, 2I and 4I, all the things are mentioned over there. Okay, copy down this question. So now we'll, before starting this one, we'll name this as A, B, C, D. Okay, this is A, B, C and D. So what is the first step we do in the calculation? Fixed end moments, isn't it? So fixed end moments, so MFAB is equal to how much? Minus WL square by 12, right? So minus, what is W over there? 8 into, what is the span? Divided by 12. Tell me this value. 3 minus 3. Yes. Tell me clearly. 13 point. Yes. Check it once again. 13.5 kilonewton. It's not per meter. Kilonewton meter. Similarly, what about MFBA? Plus WL square by 12, which is equal to plus 8 into 4.5 square divided by 12 is equal to plus 13.5 kilonewton meter. Next, what about MFBC minus WAB square by L square? Minus W is how much? 9.6 into A is 4.5 into 1.5 square divided by 6 square, right? Yes, tell me the value. Minus 2.7 kilonewton meter. What about MFCB plus WA square B by L square, that is plus 9.6 into 4.5 square into 1.5 divided by 6 square. How much? 8.1. 8.1 kilonewton meter. What about MFCD? MFDC? 0, right? MFCD and MFDC will be equal to 0. Why 0? There is no lateral loading, right? There is no load. It is entirely open. No load from the left side or neither from the right side or left side. Okay. So for this we have calculated now. After that we have to go with moment distribution factor, isn't it? That is, we have to calculate distribution factor for both the joints. Okay. Copy now. What is the next step we do? We go for distribution factor. So if you see carefully, observe this figure carefully, it is same like your continuous beam, isn't it? It is like a continuous beam, AB, CD. So we'll try to solve this one in opening these two columns like that. Okay. So now see here, distribution factor. So how many joints are there, you tell me? Joints, then member, then relative stiffness, then total relative stiffness, then distribution factor. Relative stiffness is denoted by K. This is sigma K, and distribution factor is K by sigma K. Now we'll move to the first joint, that is B. We have BA and BC. Right? So if you see carefully, B to A, it is fixed, right? So B to A is fixed means what will be the relative stiffness? I by L. What about BC? See here, B to C, again we have one more support here. So it will be fixed. We will consider that as fixed. So it will be I by L. I by L. So for BA, I is 2I by 4.5. Tell me this value. 0.444, right? I. Yes. Next, what about this one? It is 4I by how much? 0.667 I. Now you add these two terms to get total relative stiffness. Yes. 1.11 I. Okay, 1.11 I. Now what will be the distribution factor for this one? 0.444 divided by 0.4. And what about next one? Only 0.4 or 0.44? Only 0.4. Okay. Then this will be 0.6. Always remember you should get 1, approximately 1 when you add those two distribution factors. Next is C. So we have C to B, then C to D. What about C to B? I by L, which is equal to, I is 4I by 6, which is equal to how much? 0.667 I. Next CD is again I by L. I by 4.5. Tell me the value. 0.222 I. Add these two values. 0.889 I. Next, what will be the distribution factor for CB? 0.75. This is 0.75 and this will be 0.25. Okay. Able to understand? Yes, copy down. We'll move to moment distribution table. Okay. So for the calculation of our final moments, we need moment distribution table, isn't it? So it is fixed at this joint, that is A, right? I am opening that entire frame. Then here it is B, C, and here it is fixed, right? So it is D. Now what is the first thing we do in your moment distribution table? Distribution factor. So what is the distribution factors we got? For BA 0.4, 0.6. What about this one? 0.75 and 0.25. These are the two distribution factors we got for this frame. This is distribution factor. After writing distribution factor, we write our fixed end moments. What are the fixed end moments we have for MFAB? Minus 13.5 and this is plus 13.5. What about BC? Minus 2.7 and this one is plus 8.1. This is 0 and this is also 0. These are our fixed end moments. Now as soon as you write fixed end moments, we have to check whether we have any hinge support at the extreme corner. Do we have any hinge support? No hinge support. So we can directly start our calculation, okay, or balancing. So we'll start our balancing. How to balance? Yes, do this one. 13.5 minus 2.7 is how much? 10.8. So whether the value is plus or minus? Plus. So 10.8 is plus. So we'll make it as minus. So minus 10.8 into 0.4 is how much? Minus 4.32. Next value is 2 point minus 2.59. Okay, next see here, we have plus 8.1 plus 0 is again, I am writing here 8.1, it is plus, so we will make it as minus. So minus 8.1 into 0.75, 6.07 minus, right? Why? Because we have changed its sign. Next is 0. Why 0? 2 point minus 2.02. What about here? No need of balancing over here. So this step is known as balancing. Okay. So as soon as you balance, what you will do? You draw a line and add carryover moment. So see here, shall I send this value here? Yes. Why? Because it is fixed. Tell me this value minus 2.16. Yes. Here it will be 0. Then we'll take this value and we'll send this value minus 3 point how much? 02. Yes. 6.48. This value. Then who told me this 2.59? Minus 6.48. This one is minus 6.48. So how we got this one? 10.8 minus 10.8 into 0.6 is how much? 6.48. Okay. Now tell me this value. 6.07 divided by 2 is how much? 3.03. This is 3 point minus 3.24. What about here? 0 and minus 2 point minus 1.01. This is carry over moment, right? So again we have difference here, right? So what you will do? 0 minus 3.03 is how much? Add it, you will get minus 3.03. To convert this to positive, so 3.03 into 0.4, 1.21. Next is again plus 3.03 into 1.81. Here you see we have minus 3.24, right? So we'll convert it to positive. Plus 3.24 into 0.75. 2.43. Next. 0.81. Here no need to do anything. So this step is your balancing. So as soon as we balance, what we do? We start our carryover moment, right? 0.605, and here we'll be having 0, then here 1.21, and here 0.905. Next here 0.405. This is carryover moment. Now if you see these values carefully, it is again 1. Here also it is 0.9. So we'll do it once again so that we can get 0.0, at least 0.0 something. Okay. So again we'll do the balancing. 0 plus 1.21 is how much again? 1.21. So we'll make it as minus. So minus 1.21 into 0.4. Minus 0.484. Next. Minus 0.726. Here also we have 0.905. So 0.905 will make it as minus. Now you do this one. 0.678 minus. Then here minus 0.226. This is nothing. So this step is known as your balancing, isn't it? So after balancing, again what we have to do? We have to provide carryover moment. So here what will happen? Minus 0.242. This is 0. And here 0.678 divided by 2 is how much? 0. 0. Minus this one, right? 339 minus 0.339 and 363. Again 0 and minus 0.113. This is carryover moment. Now again if you see here, if after carryover moment, again see there is slightly, we have to again do something so that we can get 0.0, right? So again do this one, balancing. So minus 0.339 is this file, will make it positive. 0.1356. This one? Yes. 0.135. Okay. Next. 0.203. Next here it is minus 0.363. It is minus, so we'll make it plus. 0.272. Next is 0.09. Here it is nothing, so this step is balancing. So after balancing again, carryover moment 0.067. Next is 0 here, 0.11613, 0.136, right? Next here 0.101. This is 0 and here it will be 0.045. So this is carryover moment. Now see again we have 0.13 and 0.1. If we solve, we'll get the closest value here. The final value will be the closest one. Okay. So we'll do one step and we'll close this one. It's up to us. If the thing is, if you go as closer as possible, then you will get the final value is both the MBA and MBC will be same. Okay. So we'll do it once again, balancing. So this will be 0.136 is positive, so we'll make it negative. Minus 0.05. Next. 0.08. Minus 0.08. Next here it is 0. It is plus 0.0110. 0.101 will make it as minus. Minus 0.07. Next is 0.025. Minus, yes. So here no need of doing anything. So now this is balancing. Now you do carryover moment. Okay. So this will be how much? 0.025 minus. This is 0. What about this one? minus 0.035. This is minus 0.04. This is 0 and minus 0.012. 12 will write. Okay, now you add all these values. Where? 375. Now you add these values. From where you will add now? From the top only you should add. Okay. So these are final moments. Tell me the value. So these are the final values, that is capital MAB, MBA, MBC, MCB, MCD and finally MDC. Okay, copy down these values. Calculated final moments, that is MAB, MBA, all those values. We have not finished our problem so far. Okay, why? Because that is entirely sway moments or non-sway moments, isn't it? Now we have to consider sway moments. Okay, before that what we have to do, what we will do now, you see here. If you see the frame carefully, the entire frame is trying to get pushed towards right side, isn't it? This frame, we have a horizontal loading, right? So our frame is trying to get deflected in which direction? Right direction, isn't it? So now I will draw the frame here once again. This is our frame, right? And we have a loading of 8 kilonewton per meter and 9.6 kilonewton. Okay. Now see here, because of this horizontal loading, horizontal pressure on the frame, my frame is trying to get deflected towards right side. Okay. So this is point A and this is point B. Now I have reactions on fixed support, right? One reaction will be exactly in horizontal direction. I will name this as HA. Similarly, I will be having one more horizontal reaction, that is HB. Okay. We are not taking vertical reactions because we are bothered about the sway. Okay. Downward or upward direction reactions. We are bothered about horizontal forces now. Okay. Now we got reactions HA and HB. Okay. Now when my frame is trying, how the frame will get deflected? In this direction. To stop that deflection, what happens? We need to provide. I want to stop this sway. Okay. So what I will do? We'll try to add one force here. Okay. If you apply one force, what happens here? My frame will not sway. Okay. What is that force? I am assuming that force as P. Okay. I am assuming that force as P. The building is trying to get deflected in the left side. Okay. So I am assuming that I will apply one force here so that my building will be in its original position. That is in equilibrium. Our entire buildings are in equilibrium, isn't it? It is not moving. Sigma x is equal to 0, sigma y is equal to 0, sigma m is also equal to 0 there, right? In this entire building, sigma x, sigma y and sigma m is equal to 0. So that is why in this frame also, what I am doing, since it is trying to get deflected in this direction, I am applying one more force. Okay, that is P. Now we will calculate what is P. Okay, here we have to calculate P, HB and HA. How to calculate that? You see now. Simply sigma x is equal to 0. So sigma x is equal to 0 means minus HA minus HB minus P. We have one force which is going in right direction, that is plus 8 into 4.5. Right? You agree with this one? Yes. Equal to 0. So now tell me, minus HA minus HB minus P plus how much this one? 36 is equal to 0. Call this as equation number 1. So this is this is D, no, in our problem. This is HD, this is B and C. So we'll name this as HD and this also as HD. Alright, now moment of all forces about point B is equal to 0. Can we do it? Yes. But before that, what I will do, I will consider only span AB. Span AB. This is B and A. We have here what? HA. We have a UDL over here of intensity 8 kilonewton per meter. Okay. And also if you are considering only span AB and we are calculating what? Moment here. So we have final moments, isn't it? What are those final moments? MAB and MBA. This MBA is going in anti-clockwise direction. So that is 15.25 and this one is going in clockwise direction, right? 9.99. Okay, agree with this one? What I am doing, I am calculating moment at B, but I am considering only vertical span, that is span AB. Okay, now can you calculate moment about B? Yes. HA into 4.5, moment at B, HA into 4.5 minus 8 into 4.5 into 4.5 by 2. Remaining we have these moments also, right? What are those moments? Okay, plus 9.99 minus 25 is equal to 0. So with the help of this equation we can calculate our HA. Now can you tell me the value of HA directly here? Minus 5.26 kilonewton. Able to follow? Yes. Now we'll go for moment of all forces. You copied on this one, then we'll go for span CD. We assumed our direction correctly, right? The direction will be exactly in negative x direction, but we got minus there in previously, so it is not correct. It should be plus. Okay. We will consider another span, that is CD. Span CD. So in case of span CD, we have one horizontal reaction, that is HD, and one force P at C. This is point D. And do we have any other force? No force. Why we are considering separately span AB and span CD? Because this moment, summation moments of all forces about point C is equal to 0 is valid only for single span. Bending moment is valid for entire frame and continuous beam, but here it is valid for only single span. That is why we are taking 1 span. So what will be about, what happens if you take moment at this point? See, we have moments also, right? What are the moments? What is MDC? It is anti-clockwise or clockwise?
Plus 0.685.
Yes? Plus or minus?
Plus 0.685. 0.685.
Yes, whether it is plus or minus, you tell. Minus 0.68. What about this one? MCD? Minus 1.37, 367 or 37, both are same. Okay, understood? So both are anti-clockwise, that is both are negative, right? So this is also anti-clockwise, this is also anti-clockwise. Why anti-clockwise? Since the frame is trying to get deflected on the right side, so this part will create anti-clockwise moment to make it in its original position, right? So now HD into 4.5 force into perpendicular distance is 4.5. Then here minus 0.68 minus 1.37 is equal to 0. What about this force? This force P will become 0, right? Because we are calculating at that point C. So what will be the value of HD? Tell me the correct value.
0.45.
Yes, 0.455 or 55? 45, okay. Plus or minus? Plus. Okay. 0.45556, whatever it may be. Now we can substitute the value of HD and HA in that equation number 1, right? What is that equation? Minus HA minus HD minus P plus 36 is equal to 0, right? Yes. Substitute the value of HA, substitute the value of HD, send this term towards right hand side. So what is the value of HA we got? Minus 19.17. Why minus? Because it is minus HA. Then minus 0.45 plus 36 is equal to P. So what is the value of P now? 17.28 plus, check it once. 36 minus 19.17 minus 0.45. 16.38 kilonewton. Okay, we got the value of P now. Okay, so we'll stop our calculation here. Okay, now tomorrow we'll take moment ratios. Okay, till here you have understood, right? What are the extra things we have done when compared to our previous problem? We have added sigma x, we have added sigma m, we have added sigma c. Okay, these are the 3 add-ons which we have done. We have calculated the value of HA, HD in this problem. Especially in the previous problems we have not calculated horizontal reactions, isn't it? Right. Copy down this one. Remaining problem will be continued in the next class. Okay.